Hello everybody, I'm Markus Waiblinger from ZEISS and I'm the product manager for the eBeam repair system MERIT. Today we talk about how low energetic electrons help us to help the industry to continue shrinking their products. For those of you who are not so familiar with mask repair, let me give you a brief introduction how mask repair works. On the left side we see a defect, and the only thing the operator has to do is he has to identify an area which is without defect. And these two areas then are compared, and the delta is the so-called repair shape. And this is the area the repair tool then will repair. The principle of mask repair is quite easy. So we put a precursor on the defect and activate this precursor using an electron beam. And then we have two possible reactions. One reaction is that the precursor reacts with the surface, creating a volatile product. That means we etch something away, or the precursor reacts with the surface and we get some material which is growing. So this is deposition. And with this technique, we can repair all kinds of defects on photomasks. What is the limit of eBeam-based photomask repair? This is the resolution, the repair resolution what we have. And this is defined by the diameter of the primary beam and the backscattered electrons. And there are several technologies how we can reduce these radius. One technology is to switch from electrons to ions. Ions have a different characteristic in sputtering around. Or we take away energy from the electrons that they can't bounce around, and this is then reducing the effective radius as well. In order to benchmark which technology is best for the industry, we set up two systems in our R&D fab. One is a low energetic eBeam system, the other is a so-called GFIS system, both equipped with gas injection systems, in order to compare what are the benefits of this technology, what are the problems, which problems can be overcome, which not. And the long story short, we at ZEISS, we decided to pursue low energetic electrons. The mechanism behind that is quite simple. So we have an electron beam hitting material, so we have electrons bounce around, and some of these electrons bounce back to the surface. And this area where the electron bounces back to the surface needs to be reduced. If we now take away energy from the electrons, the interaction volume gets smaller and smaller. And if the interaction volume gets smaller and smaller, the surface radius gets smaller as well, and this increases the resolution of the repair process. Until today, typically energies which are used are in the region of 1 kiloelectron volt. So if we go down, we can see that we can dramatically decrease the repair diameter and so increase the resolution what we have. And here's a sketch how our tool works. So on the upper part, we see the source for the electrons. These electrons are then collected that we have a very sharp beam with a small diameter and that the beam has a low energy. And these electrons then hit the surface of the photomask where the defect is. If we use high energetic electrons, then the surface volume or the interaction radius is quite large, so we smear out during the repair process. If we now reduce the energy, then the radius is quite small and we can repair defects very, very sharp and can reconstruct sharp features, so we have a high fidelity for pattern reconstruction. Last but not least, low energy electrons carry not so much energy, so we have less damage of the surface of the photomask. So here we see a Monte Carlo simulation of an isolated defect, what we want to etch away. And we see in the simulation first that the electrons bounce around, and we also see that the electrons reach the surface, areas we don't want to repair. And of course, these precursor molecules sitting on the quartz surface don't know if they're activated by a primary or a secondary electron. So the red area shows this is the area where we have some reaction which is unwanted. If we now just reduce the primary energy by a factor of 2, we see that the electrons reaching the surface are significantly less, and that the radius where we damage the surface is dramatically reduced just by the factor of 2. And the background is that this is a nonlinear effect. So sometimes we get something back from nature when we go in the right direction. Another effect is the electron bounce around. That means we have to apply a process bias. And especially for small defects, for isolated defects, if we apply a process bias which is larger than the defect itself, we can't repair it at all because the bias is larger than the repair shape. If we now reduce the energy, the process bias we have to apply is significantly smaller. So this is enabling us to repair very, very small defects. The question is, how does this look in real life? So here we have an example of a CPL mask, so quartz on quartz, and we have a line shortening of approximately 50 nanometer. And we applied a 0-pixel bias process. And we see that after repair, both lines have the same length and that the surface damage is almost invisible. So this is something I would rate as a very successful repair. For photomasks, another problem is on the horizon. This is the numbers of photomasks we have to address. At the beginning of photomask technology, we have 2 different kinds of materials. Today we fight with approximately 50 materials which are used in production. For a chemical process which is induced by an eBeam, we have to find a chemical which is suitable for this technology and which fits to the chemical of the photomask that we can repair this kind of material. And one of the so-called disadvantages people say we have with this kind of technology is the selectivity. And what I show you here are the selectivity of selected processes. So for EOV we have 75:1. For COG we have more than 100:1. For MOSI 2:1. And for the high durable and high transmission materials we are above 8:1. So the selectivities we have when we used chemical-induced eBeam-induced chemical reactions, we can increase the selectivity above everything what we know from ion-based processes, which are typically below 10:1. On this slide, you see the selectivity of one of the most prominent materials. This is the high durable phase-shifting material A6L2, and here we achieve a selectivity of 10:1. So what is the benefit of selectivity? So on the left side, you see the MOSI, on the right side we see the quartz, and we placed per purpose a repair shape 50% on the MOSI and 50% on the quartz, and etched the complete area until the MOSI is gone. And we see, yes, we etch a little bit of the quartz, but the material we etched away is not enough that we get an error what would print an AIMS or what would print in a wafer print. So it's driving us to the process window border, but we stay still within the process window, which means that even this defect is within specification. So how does this look like on real defects? So what we see here is an extension on a high transmission, high durable material. And we repaired it, and we see that in the SEM image it looks quite nice. And when we do an AIMS verification, we see that even through focus, we managed to bring the delta CD below 2% even through focus. If this works, well, then we ask our engineers, well, can you do something else? Can you do something more challenging? So we tried an extension and a bridge in one step. And we see in the post-repair image that we were able to repair this successfully. It looks quite nice. And even the AIMS repair verification show that even for this more complicated defect, we managed to reconstruct the delta CD below 2% even through focus. Then we tried something which is rated as unrepairable at all. This is a 10 nanometer extension, and we had some discussion if this is relevant at all. So we did, before we repaired it, an AIMS measurement, and yes, we have to repair it. So this will give a delta CD of more than 8%, which is exceeding all specifications we know for wafer prints. So after repair, we see that the repair area looks very nice. So we see no collateral damage. And when we verify it in AIMS, we see that we stay below 2.5%. So a very successful repair. So Bringing down the energy enables us to increase the repair resolution, and putting this in a new tool generation together with a chemical toolbox enables us to address a very broad variety of mask blanks, and that's the reason why we put this together into our new generation repair tool called ZEISS MERITneXT. Thank you very much for your attention.